All right, welcome to Physics 2425, Lecture 13A, Torque and Rotational Equilibrium. So when we started looking at linear motion at the beginning of term, we started with kinematics, then we moved on to forces and then work and energy. We're kind of going through that exact same progression, but this time with rotation. So we did rotational kinematics, and the next thing we would have done is, in linear terms, would have been forces and equilibrium. Well, now we have torque and equilibrium. So torque is going to be our rotational equivalent of force. So when we look at force, our angular accelerations are caused by forces, but the difference is it matters where and how the forces are applied. So picture that you have a door here. So this door is a top-down view. Your hinge is the axis of rotation. And you apply a force at some distance. This position vector R is often called the lever arm. Okay, we think of like simple machines, you have levers. And the angle at which you apply the force, those are the values that are going to matter. So when we take a look, the smaller the force, the smaller the rotation is going to be. And that just kind of makes sense. So that kind of goes along with linear motion. When we look at the position vector R, the closer the force is to the axis of rotation, the smaller the rotation. And if you think about it, if I were to try and push right on the hinge, this door is not going to rotate. You cannot open a door by pushing on the hinge. It does not work. So that position vector matters as well, where the force is applied. And the angle matters, because if you want to open a door, if I were to push, say, parallel to the door, I'm not going to be able to open this door. The optimum angle is going to be at this 90-degree angle between that lever arm vector. So if the less perpendicular your force is, the less your rotation is going to be overall. So putting all of those together, we are really looking at force and the position vector and this angle. And we want our forces to be perpendicular to each other. So therefore, our torque is actually a cross product. So the cross product of the radius vector and the force vector, or the position vector. Now, with cross products, the order does matter. So when you solve the cross product, the position vector R does have to go first, with the force coming off second. When we look at that angle theta is measured from the extension of the position vector and force. That's where the official theta is. Now, in 2 dimensions, you can simplify this down into RF times sine of the angle theta. But you have to be careful, because in order to use this trig simplification for the cross product, your angle theta has to be this specific angle. And in a problem, they might not give you that angle. So for example, if they give you this angle right here, if that is what they are calling theta, that is not the same angle. And if you try and plug it in here, you're going to get the wrong answer. So a better way to kind of think about the cross product is you take torque and you take either the perpendicular component to F, or you take R times the component of the force that's perpendicular to the R. So what I would do is I would take this force, say here, and break it up into 2 components. So this component right here would be my F perpendicular, because it's perpendicular to R, and this side over here would be parallel. So if I look at this green theta right here, my F perpendicular is the adjacent side of that. So I do R F perpendicular, that's going to be R times F cosine of my angle theta. So, and that's because this theta here is not the same as the theta that's defined here. So that's an example of why I definitely do not use just kind of like the sine theta there for my cross product, because it can cause problems. Instead, I actually do the trig itself and find the components that are perpendicular. The other way you could do is using this equation right here with the R perpendicular times F. So in that case, what you're looking for, I'm going to simplify this down again, is if you're going to use that version, you want to find the component of R that is perpendicular. So what you do is you make a triangle here with R. So R is the hypotenuse of this triangle. And then you would have a component of R here that's perpendicular, which they're calling D. And you can see that that is going to be perpendicular to F. And then this other section right here would be R parallel. So if you were to kind of look at that angle, you've got your theta here. This is my theta right there, because that's the opposite side of this parallel bisector kind of geometry thing. So if I make that my angle theta, this R perpendicular is the opposite side. So my torque would be R perpendicular times F, which in this case, using this same theta here, would give me R sine theta times F, where R sine theta is R perpendicular. So you can work either one of those, or you can solve the cross product if you're given unit vector notation and so forth, using matrices or your preferred method for the cross product. So the units of torque are the Newton meter. So you're taking a force times the distance, so newtons times meters. The big difference here is this Newton meter does not equal joules. Okay, when we did work also has units of Newton meters, and it was equal to energy in joules. You cannot replace a Newton meter with a joule here. That's one of the reasons why you cannot just look at units and figure out how to do your math. In general, what the cross product tells us is that only the components of the force that's perpendicular to the position vector contributes to the magnitude of torque, and the resulting torque is perpendicular to both the force and the radius. So when we look at that cross product, let's say I have this force being applied here, that's going to cause a rotation in this disk. That rotation is going to be in the counterclockwise direction, but my torque is not counterclockwise. My torque, using the right-hand rule, actually comes out, sticking up out of the page. So you can use that right-hand rule by pointing your fingers in the direction of the first vector, which is R, rotating your palm so it faces the force, and then your thumb points to the direction of the torque. Or the nice shortcut way is use the same thing we did for angular velocity. Curl your fingers in the direction that the force is trying to cause a rotation, and then your thumb points perpendicular from that. So the direction of that torque, like I said, is going to be positive if you have counterclockwise. It's going to be negative if you have clockwise. You can use the right-hand rule to prove that. So even though technically the torque doesn't point clockwise or counterclockwise, if you think of counterclockwise as being positive torque and clockwise as being negative torque, you'll work out fine. But that torque is always perpendicular to the plane of rotation. And this is just a reminder of kind of the formula for how you can do those calculations in 2 dimensions. You can also therefore have net torque, just like we have individual forces. If multiple forces are acting, you have a net force. I can have multiple torques acting. So for example, if I have this random object here and point O here is my axis of rotation, and I'm applying these 2 different forces, you could find the torque due to the first force and the torque due to the second force and add them up. Now you can see that this first force, F1, is trying to cause a rotation in the counterclockwise direction, whereas this F2 is trying to cause a torque in the clockwise direction. So those will be different signs. This one would be a positive torque. The F2 would be cause a negative torque. So if our net torque is 0, then you have no angular acceleration. It means you're either rotating at a constant speed or not rotating at all. We would call this rotational equilibrium. If your net torque does not equal 0, you will have an angular velocity that is changing, which means you will have an angular acceleration. So your angular acceleration does not equal 0. So you will be changing angular speeds and or directions around the circle. So here's an example of how we could calculate net torque. So we have 3 different forces acting on a rod. We're going to assume that the axis of rotation is 0.0. So we're going to have an axis of rotation here through 0.0. We want to find the torque. So basically the first thing I do is I figure out which torques are positive and negative. So if I kind of look, if I apply this torque here, this 25 Newton torque, it looks like it's going to cause a rotation in the counterclockwise direction. What I would do is it's kind of silly, I don't know. I kind of treat my elbow like the axis of rotation. So like if I hold up my left arm at that picture and then I try and push my arm where those forces are. So if I try and kind of push up at an angle, I can see that that's going to cause my hand to rotate in the counterclockwise direction. So you might be able to try that if you're having a hard time like picturing it in your brain, actually treating your elbow like that axis and then treating your arm like the rod and trying to push it. This 10 Newton force, it looks like it is causing a clockwise rotation. And this 30 Newton force is acting at the axis of rotation. Since our torque is equal to R cross F, and R is the vector drawn from the axis of rotation to the point where the force is applied, if I have a force applied at the axis of rotation, the torque to that force is 0. So that force is not contributing to the torque at all. So I'm going to call the 25 Newton force, force 1, and the 10 Newton force, force 2. And so therefore, in this case, my net torque is going to be the torque due to the first one, which is positive, and I'm going to subtract the torque due to the second one. So I'm going to treat this guy as being inherently negative, this guy as being inherently positive, but I'm going to, when I write my equation, I'm going to write the negative there. So that way I don't have to worry about the signs again. I've already written out my signs. So then I go through and I say I'm going to define in 2 dimensions that torque 1 is going to be R1 times F1 perpendicular. And then torque 2 is going to be R2 force 2 perpendicular. So when I draw my diagrams, I do need to make sure that my forces are starting on the object, which these are doing, and then I need to actually draw in those lever arms. So I'm going to draw in R1 for that one. And then I'm going to draw in R2 there. Now, in this case, it's not really a big deal because they give me R1, it's going to be 2 meters. And they give me R2, it's going to be 4 meters. But sometimes they give you dimensions that are not the same as the lever arm. So drawing in those lever arm vectors on your diagram will actually help you figure those types of problems out. So R1, I'll just write down here is 2.0 meters, and R2 is going to be 4.0 meters. F1 is 25 newtons, and F2 is going to be 10 newtons. Now, if you look at these 2 forces, neither of them are acting perpendicular. So what I need to do is find the component of these forces that's perpendicular to the lever arms. So for the first force, I'm going to make a triangle here. And so F1 perpendicular is going to be this side right there. It's the adjacent side of the triangle where my 25 newtons is the hypotenuse. So that F1 perpendicular is going to be F1 cosine of theta 1. So I'm going to call this guy theta 1. And then over here for R2, when I look at that guy, I'm going to use this triangle here. So I'm going to have the perpendicular component to the radius is actually going to be the opposite side right here. So that's going to be F2 perpendicular. and that's the opposite side. So I'm going to subtract R2 F2, but that one's going to be based on sine of theta 2. And so that's going to be theta 2 right there. So I'm going to add in that theta 2 is 20 degrees and theta 1 is 30 degrees. So when I go through, I've already taken care of the negative sign because F2 is in the opposite direction of the torque for F1. So then I plug in R1 is going to be 2.0 meters. F1 is 25 newtons. Cosine of theta 1, which is 30 degrees, minus my R2 is 4.0 meters. F2 is 10 newtons. And then sine of 20 degrees for theta 2. So I find that when I calculate the net torque, I get a net torque that is about 29.6 Newton meters. And it calculated out as positive. So the torque due to F1 is going to be larger because it has a bigger force and it's more perpendicular even though it's closer. So this positive torque tells me that the direction of rotation is going to be counterclockwise. So that is how you solve a net torque problem. So we can then define static equilibrium. So if you're in static equilibrium, then two things have to be true. You have to be in both translational equilibrium and rotational equilibrium. So translational equilibrium is when the linear acceleration of the center of mass is 0 and the angular acceleration of the object is 0. So you'll have either a constant linear speed or 0 linear speed, or a constant or 0 angular speed for rotational equilibrium. But to be in static equilibrium, static means no motion at all, so you're going to have the constant options there. So translational equilibrium, linear acceleration is 0, rotational equilibrium, angular acceleration is 0, static equilibrium, both of those conditions have to be met and you can't be moving. Otherwise, you could be in dynamic equilibrium and have both of those conditions still be met. But in that case, you're going to be constant but non-zero. In this case, we're going to be constantly 0 for static equilibrium. So static equilibrium is no motion at all, so the velocity of the center of mass is 0 and your angular speed is 0. Dynamic equilibrium, constant velocity, velocity of the center of mass is constant and your angular speed is constant. So an example of static equilibrium is if you have two kids on a seesaw and the seesaw is balanced and at rest. This is a very common problem. So each of these kids is going to be creating a torque. Those torques are going to be in opposite direction about the axis of rotation, the fulcrum. Additionally, there are downward forces from the kids getting balanced by the upward force of the fulcrum. So you have both net force being 0 and net torque being 0. Whereas if you have dynamic equilibrium, picture that you have a wheel rolling at a constant speed. If it's rolling at a constant speed, it's linear speed of the center of mass. It's translating at a constant speed. But then the angular speed is going to also be constant if you're going at a constant speed. So you can be in dynamic equilibrium as well. So then we can relate this to the center of gravity. It's a little different than the center of mass. So the center of gravity is based on where the net torque would be 0 on the object. So a little different than the center of mass. But they are generally going to be the exact same location. So the axis of rotation, when it's placed at the center of gravity, means that the gravitational force does not exert torque. So when you picture the gravitational force, every little tiny infinitesimally small piece of this mass has gravity acting on it. So every one of those little tiny pieces is a huge collection of point masses. And if you have in some axis of rotation, then each of those gravitational forces has its own lever arm, its own force, and therefore a torque based on the angle that it's at. So if you were to add up all of those different torques by every infinitesimally small piece here, the center of gravity is the point where if you drew the gravitational force that at that point, and R would be the position vector to that center of gravity. If you calculate the torque by this guy, it equals the torque that you would get by adding up all of the little tiny point masses. So we do this for any non-point object. So picture kind of that seesaw idea. So let's say I have a board and I place a fulcrum that's not at the center. So if this is a uniform board, the center of gravity is going to be the same as the center of mass. And so I'm going to draw my gravitational force right there at basically a position of L/2. And then instead of having to deal with the left side of the board, what's the left side of the board doing, what's the right side of the board doing, I treat the whole board as having one gravitational force at the center of the object. And then I measure the torque based on the distance from the axis of rotation to that gravitational force. So you're going to do that. So this is really something just to kind of think in the back of your minds, that we are going to, from now on, draw one gravitational force, even if our object is long, but we're going to put it at the center of gravity, which if the object is uniform is the same as the center of mass. So if we're going and solving static equilibrium problems, there's a series of steps to follow that are very similar to our net force problems that we did before. So the first thing, you draw an extended body diagram leaving all forces at their point of contact. So this means that we no longer draw our forces at the center of the object. So if I have a force, because I have like a kid sitting here on a seesaw and I have a kid sitting here on a seesaw, I don't draw those forces at the center. I draw them exactly where they're acting. So I'm going to draw them on my seesaw exactly at the point where they are applied. Okay, so at the point of contact, we are going to choose an axis of rotation. Now, if you are in equilibrium, rotational equilibrium, it's about any possible axis of rotation. So technically, you can choose any point, say on this rod, to be the axis of rotation. But where we choose that axis of rotation can help us eliminate variables due to forces and so forth. So when we choose an axis of rotation, we don't always put it at the logical axis of rotation where it might actually be rotating about. We'll usually just pick a point where we have a lot of unknown forces, because if I put my axis of rotation, say I don't know like the mass of this kid, if I put my axis of rotation here, then this force of that kid is not creating any torque, so it won't show up in my net torque equations. It might show up in my force, it will show up in my force equations, but if I can eliminate some of the variables from my torque equations, I can go through and solve things easier. And that'll make more sense the more problems you work. You need to actually draw in those position vectors. Starting at the axis of rotation and pointing towards each of the forces. Now, the caveat on this one is you don't do this on official free body diagrams for exams, because you'll just end up cluttering it up. So if I ask you on an exam to draw a free body diagram, just draw the forces. It'll say draw the forces. Don't draw anything else, just the forces. But draw a second diagram and label more in detail. And then you'll need to determine which forces create torque and whether they're positive or negative torques based on your axis of rotation. You'll need to write net force and net torque equations. In more complicated problems, you might have net force equations in both the x and y direction and a net torque equation. And then you'll have to solve your system for your unknowns. Of course, the best way to do that is to do that non-numerically, only plugging numbers in at the end. So let's take a look at an example. So we have a seesaw problem. These are some of the more straightforward, easy problems because they don't involve motion in the x direction, just in the y direction. So we have a uniform board with a mass and a length, and there's a father and daughter with two different masses at different positions. And the support is in the center of the board, and the daughter is a distance of 2 meters from the center. So what we know is we have basically this fulcrum right here, and that's going to be our natural kind of axis of rotation. It's also going to be a point where we have an unknown force, because the normal force here of the fulcrum on the board is an unknown force. We're going to assume that the daughter has a force that is acting down on, I'm going to call that FD, for a force of the daughter acting down on the board. The father is going to have a force, I'm going to call that FF, for F of the father, that is going to be pointing down. Now notice in the picture that the father is located closer to the axis of rotation than the daughter. And that's going to be most likely going to happen because he's going to have a bigger mass, so his force is going to be larger. So in order for their torques to balance out, they're going to need to have different distances to have those torques equal to each other. Now, additionally, the board itself has a mass, so there's going to be a gravitational force. Now, it tells us the support is in the center, so that gravitational force is acting in the exact same location as that normal force due to the fulcrum. So I want to find the magnitude of the force exerted by the support on the board. So that's this normal force right here. So normally what I would do is when I'm looking at forces is I'd write a net force equation in the y direction. So my net force in the y direction is going to be my upward force, Fn, minus my downward forces, the force of the daughter, the force of gravity, and the force of the father. And those have to equal to 0 because we're in equilibrium. So if I wanted to find that normal force, I would need the force of the daughter, the gravitational force, and the force of the father. So if I was to look at that, I only have M's and G's and things for that. So, and I've got like a distance for there. So my normal force here would have to equal the force of the daughter plus the gravitational force plus the force of the father. Now, technically, these forces here are not gravitational forces because gravitational forces are the earth on the daughter. But because we're in equilibrium, the gravitational force of the earth on the daughter has to equal the force of the board pushing the daughter back up. So these are actually going to be equal to the gravitational forces of the daughter and the gravitational forces of the father because you're in equilibrium. So if the gravity is pulling down, the board's pushing them back up and they have to be equal. And then the force of the daughter on the board is equal and opposite the force of the board on the daughter. So we're all good. So don't label these forces of the people acting on the board as gravitational forces because that's only if this earth specifically acts on the object. But they're going to be equivalent. So I'm going to say that my normal force is going to equal the mass of the daughter, which is little m, times g. The force of the father, oh, I wrote Fg next. So that's going to be mass of the board times g. And then the force of the father is going to be big M times g. Now, I don't have any values for this, so I can just summarize this as going to be little m plus mass of the board plus big M all times g. So that is going to be my normal force. I don't have more numbers than that in this case. So I want to now find where the father should sit to balance the system at rest. So this is really the new part. So I can't use my net force equation to find position, okay, because I'm looking for where the father should sit. This is where torque has to come into play. So in order to analyze torque, I need to add in those lever arms. So I'm going to add in R for the daughter and R for the father. Now we know that R for the daughter is 2 meters, so that is a known value. I'm going to choose an axis of rotation. I can technically pick anywhere along the board as my axis of rotation for analyzing torque, but it makes more sense to put it where I have unknown forces or where I've got a lot of forces so that I don't have those forces create torque. So if I do create my axis of rotation to be where the fulcrum is, then the normal force exerts no torque. The gravitational force exerts no torque. So therefore, I have a torque being caused by the daughter trying to cause a counterclockwise rotation, and a torque by the father trying to cause a clockwise rotation. So I can therefore write an equation that says that my net torque is equal to the torque by the daughter minus the torque due to the father, and that has to add up to 0. So basically, the torque due to the daughter has to equal the torque due to the father. The torque due to the daughter, I'm going to assume that these are 90-degree angles. So you have a 90-degree angle for both of these. So those torques are just R times F. So torque for the daughter is going to be R for the daughter, F for the daughter. Torque for the father is going to be R for the father, force for the father. And then those forces are equal to their gravitational forces. So R for the daughter is going to be little m times g. R for the father times the force of the father is going to be big M times g. So the first thing I noticed is that the g actually does cancel out here. And then if I'm looking for R for the father is going to be R for the daughter times mass of the daughter divided by the big mass of the father. So R for the daughter we know. Okay, it's at a distance of 2 meters, but I actually don't know the mass of the daughter and the mass of the father. But what I do know is that the larger the mass of the father, the smaller the distance needs to be. So basically, as his mass gets larger and larger, big beer belly here, then he's going to have to sit closer and closer in order to balance her torque. So that's an example of static equilibrium. Now, more complicated problems are going to involve both forces in the x and the y direction. This problem also kind of weird. These problems are kind of weird. They've got a little hybrid thing going on where they don't have combination of numbers and not numbers. So let's just ignore this number here, because that's the only number they give us. So let's not worry about that. So we have a ladder here, and it's resting against a smooth wall. So whenever they say smooth, smooth is going to tell us that our friction is 0. So there's no friction with the wall. Okay, the ladder itself does have a mass of m, and there is friction with the ground. So this is, or they might say rough. So there's some friction here with the ground. And we want to find the minimum angle theta here at which we can put the ladder so the ladder does not slip. So we're going to need to go through and use equilibrium. So we're going to have to think about all the forces that are acting. Well, it's a uniform ladder, so we can assume that the gravitational force is acting on the center of mass, which is the center of the ladder. So I'm going to draw the gravitational force as coming straight down from the center of that ladder. The ground is going to be pushing upwards, creating a normal force. I'm going to call that FNF for FN of the floor. The wall is also pushing out, so I'm going to call that FN of the wall. Otherwise, this ladder would be falling through the wall. And then there needs to be a source of friction at the floor, but where does that friction point? Does the friction point to the left or to the right? Well, if you think about it, this ladder, if it's trying to fall, the bottom of the ladder is going to be moving to the left. The friction has to oppose that. So that means that our friction force is going to be acting to the right. So I'm going to call that the friction force of the floor. So F of the floor. Curly F for friction, F for the floor. So those are my forces. So if I was to write a net force equation, I could write a net force equation in the y direction. And that's going to be Fn of the floor minus Fg, and that has to equal 0. I could have a net force in the x direction, and that would have to be the force of friction minus the normal force at the wall, and that has to also be 0. So If I wanted to find the angle theta, which the ladder doesn't slip, it's possible that I could do this with forces and not even need to worry about torque. Well, let's kind of see what we can do here in terms of what we know and what we don't know. So Fn of the floor has to equal our gravitational force, which is just m times g. Okay, well, that's good to know. I know mass, I know g. So it's possible that I could therefore find the normal force of the floor. The force of friction of the floor, I'm looking at the point where the ladder does not slip, so that means I can assume that the force of friction of the floor is going to be mu Fn. I'm going to call that mu S, and that's going to be Fn of the floor. And that's going to equal the normal force of the wall. So, so far, I don't actually have any angles in these equations. So if I'm looking for theta, I'm kind of running out of problems here. I can plug in over here that Fn of the floor is mg. So I can say that mu S times mg is equal to Fnw. But there's no theta in this equation. So I've got a problem here because just using forces, I'm not getting an angle theta because my forces are all in the x and y direction. So I'm like, this is not really helping. So I need more information. So this is where torque comes in. So if we're going to be looking at torque, we need an axis of rotation. So I can choose any point on this ladder to be the axis of rotation. But there's three likely candidates. The first candidate is going to be the actual center of mass of the ladder. That kind of makes sense. It's the middle of the ladder. If you think about it, this thing is going to fall and rotate kind of about that center point. But that's not actually my best point that I could use because I know my gravitational force and I know it's located. So I want to put my axis of rotation where I have unknown forces. Like, okay, well, I could put it here with the wall. If I do that with the wall, I don't have torque by the wall then, which is good because that's something that's unknown. And then I would have torque being caused by these other forces. And I could do that. But actually, what's easier is if I choose the floor to be my axis of rotation, because that means that neither the normal force of the floor or the friction of the floor are going to be creating any torque. So that actually creates a really simple equation for my torque. So I'm going to do that. So then I need to make sure that I draw my lever arm values in. So for my forces, so I'm going to have my gravitational force here. I'm going to call that RG. That's the lever arm for my gravitational force. And then I'm going to have a lever arm for my normal force at the wall, which I'm going to call RW for the wall. Now, these are nice values because RW for the wall is just L. And then if I look at the gravitational force, it's at the midpoint, so RG is just going to be L over 2. Now, we do have an additional problem, and that is that those forces are not perpendicular to their lever arms. So we do need to find a way to incorporate the angle, which is good because that's actually what we're missing, right? So if I take a look here, I've got a triangle right here with like where my gravitational force is and so forth. I've got the angle theta right here. I want to find the component of that gravitational force that is perpendicular to my lever arm. So there's different ways to kind of go about doing that. But one of the ways you could do is using that arrow right there. Let's see. Right there, it's a little easier to see. So if this FG is my hypotenuse, then this would be FG perpendicular to R. So that is a 90-degree angle right there. The only problem with that is that the angle that that's based on is not theta. It's 90 minus theta. And I don't want to use that. So that's actually not the triangle I want to use. So instead, I want to use this triangle over here. So I'm going to make a 90-degree right there. FG is still the hypotenuse of that. but then my FG perpendicular is going to be right here. Now, if we go through and look at these angles, this angle right here is 90 minus theta. This is a 90 degrees. So this angle right here is actually theta. Okay, so that actually works nicely for us because that makes FG perpendicular the adjacent side of that triangle. So that's going to be what's creating torque. When I come over here and try and do a similar thing, I could do a couple different triangles for FNW. If I have that as my 90 degree angle, then that would be FNW perpendicular. And if I look at this angle, that's actually the opposite angle of the bisector. So that is actually our angle theta. So my FNW here is the opposite side of that triangle. So kind of working through those angles can be a little tricky. You might want to kind of draw it out and kind of track those angles if you can yourself. So what I'm going to do is then write a net torque equation. So my net torque about this axis of rotation down here at the bottom is going to be the torque caused by this FNW is going to be causing that positive torque, and gravity is going to be causing the negative torque. So I'm going to do the torque due to FNW minus the torque due to gravity, and that has to equal 0. So the torque due to FNW has to equal the torque due to gravity. But remember, when you're working equilibrium problems, it's important that you write your equations showing that they equal 0, because that's your application of theory, that your translational equilibrium has your net force in the y direction equal to 0, the net force in the x direction equal to 0, and rotational equilibrium requires that your net torque is 0. So please don't start with this step. Please start with your equations equaling 0. The torque due to FNW is going to be R for W. Oops, sorry. The torque for FNW is going to be RW, based on what I defined here, times the force FNW, and then the perpendicular component of that. And then your torque for gravity is going to be RG, which is our L/2, times the component of gravity that is perpendicular, which is going to be this component right here. So RW, FNW, this is the opposite side based on theta, so that's going to be sine theta, is equal to RG, FG. And then this one's actually based on the cosine of theta. Sorry, I ran in a little spot over there. RW is L, so I can L FNW sine theta. RG is L/2, FG is mg, and we have cosine of theta. Notice that I can cancel an L. So I get FNW sine theta is equal to 1/2 mg cosine theta. Now we're looking for theta in terms of the things that I know. So FNW, I don't have a defined variable for that here, but we did get an expression for FNW using our x equation, so I can actually plug that in, and I'm going to bring that all over here so I have some more space. So I get FNW is going to be mu s m times g times sine theta is equal to 1/2 mg cosine theta. So m cancels, g cancels, so I get mu s sine theta is equal to 1/2 of cosine theta. I'm looking for theta, so I need to get those on the same side. I like using tangent, so I'm going to divide cosine theta on both sides. So this gives me mu s sine theta over tan theta is, sine theta over cosine theta is tan theta, and that's going to equal 1/2. So tan theta is going to equal 1/2 times mu s. So if I wanted to find theta, I take the arctan of both sides. So that is going to give me that theta is tan to the minus 1 of 1 over 2 times mu s. So if I had, oh, I actually did. That's why this works. Haha, never mind. There's a reason they didn't give me anything else besides the value for mu s. Ding, 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 ding. Because you don't need anything else. So because they give us the value for mu s, we can actually calculate the angle without knowing the mass of the ladder, the length of the ladder. We can find this value. So if I plug in tan to the minus 1 of 1 over 2 times 0.40, look at that. I get 51.3 degrees. So based on that coefficient. Now, if that coefficient was larger, then I could actually get it at a shallower angle before it slips. This one is numerical, so we have lots of numbers to work with. And this is another typical problem where you have like a beam. This time you've got like a rope supporting a beam. So kind of a combination of like the ladder and the seesaw. So when you look at all these different forces, you're going to have the beam itself is uniform and horizontal. It has a length of 8 meters. There's a weight of 200 newtons. So we can assume that this beam, because it's uniform, has a gravitational force that acts at the center of the beam. There is a cable at the end of the beam. That cable is going to be exerting a tension force. So that tension force is going to act along the angle there. And it's making a 53 degrees. There's a person with a weight of 600 newtons. So they are also going to have a force. I'm going to call that FP for F person, standing at a distance of 2 meters. That value is not on there. And we want to find the tension in the cable as well as the magnitude and direction of the force exerted by the wall on the beam. So this force of the wall on the beam is really ambiguous. And this is kind of like the hardest part of these types of problems, is figuring out where that is. So we know that if we are in equilibrium, that our net force in the x direction has to be 0. Our net force in the y direction has to be 0. And our net torque on our system has to be 0, about any possible axis of rotation. So the first thing I notice is that I have lots of forces with components in the y direction, but my tension's the only force right now that has a component in the x direction. So it has both an FTX and an FTY. So I know that if I'm going to have a net force of 0, there has to be some other force acting to the right to cancel that out. So there's going to be some force of the wall here acting on the beam that is in the x direction. I'm going to call that FW for F wall. But is there a force in the y direction? It's possible, because you have a hinge that can rotate. So it's possible that that hinge could have both an x and a y component of the forces. We don't really know. So the best thing to do so you don't make any mistakes is to assume that that resistive force at the wall always has both an x and a y component. I'm just going to arbitrarily assume that that force of the wall is going to have a component that is in the y direction, in the positive y direction. I'm going to do that just because, well, we've got 2 forces going down and only one coming up, and that one coming up's at an angle. Now, if that was a bad assumption, if there actually is no y component, then FYW or FWY will calculate as 0. If that y component of that force is actually in the downward direction, not the upward direction, it'll calculate out as negative. So it doesn't actually matter where I assume it is, the problem will fix itself. But if I assume that it's 0 and it's not 0, my whole problem will end up incorrect. So it's really important that you assume that that's going to be there. And I'm just going to pick up as my arbitrary direction. Now I'm going to assume that my axis of rotation is going to be that hinge point at the wall. Why? Because I don't know anything about that force of the wall, so I don't want it to exert any torque. Because if it was exerting torque, then that would be two forces that I would need to figure out. And I know more about all the other forces. So when I look at this problem and I set up my net force in the x direction, my net force in the x direction is going to be my upward forces, which is going to be Fty plus Fwy minus the force of the person minus the force of gravity, and that has to add up to 0. In the x direction, or so that's the y direction, sorry, net force in the y direction. In the x direction, I'm going to have to the right Fwx, to the left Ftx, and that has to be 0. And then with my net torque, if I look, these two forces are creating torques that are in the clockwise direction, so those are negatives, and the tension is going to be creating a torque that's towards the clockwise direction, so that's positive. So my net torque is going to be the torque due to tension minus the torque due to the person minus the torque due to gravity, which has to equal 0. So I've got a lot going on here, and I want to find several different things. I want to find the tension in the cable, and I want to basically find Fw. So I want to find Ft and Fw. To find Fw, I'm going to have to find both Fwx and Fwy. So I'm going to start over here with my torque equation. And the reason I'm going to start with that is because it doesn't involve that unknown force at the wall. So the torque due to tension is going to be based on the component of tension that's perpendicular to the beam, which is Fty. So that torque due to tension is going to be Fty times R for the tension. And that is going to have to equal the force of the person times R for the person plus the force of gravity times R for gravity. Those are both at 90-degree angles to the beam, so I don't have to include any components on that one. So Fty is the opposite side of the triangle. I'm going to call that one theta. So Fty is going to be Ft sine theta because it's the opposite side. RT, and that's going to equal F for the person, R for the person, plus Fg, Rg. So Ft is going to be Fp times Rp plus Fg times Rg all over sine theta times RT. And we actually know all of those values. So the force of the person is their weight. The person weighs 600 newtons. The person's located 2 meters from that axis. The gravitational force is the weight of the beam, which is 200 newtons. And the force of the beam is in the middle, so that's going to be at 4 meters. R for the tension is the whole length of the beam, so that's 8 meters times sine of 53 degrees. I just moved that, switched those orders to make it easier to write. So if you plug that in, you get approximately 313 newtons for the force of tension. So we were able to find that tension without knowing anything about how the forces of the wall are coming into play. So now we need to find the x and y components of that force of the wall. So that's where these other two equations come into play. So we're going to start over here. Fwx is going to be Ftx. Ftx is the adjacent side there, so that's going to be Ft times cosine of the angle theta. So plugging in Fwx is Ft, which is 313 newtons, times cosine of 53 degrees, which calculates out to 188 newtons. I'm just using 3 sig figs here. And then over here on the other side, Fty, I can solve for Fwy, is going to be Fp minus Fg nope, FTP plus FG, so we got to add those to the other side, minus FTY. So FW is going to be FP plus FG minus FT sine of theta. So we get FP is 600 newtons plus FG is 200 newtons minus FT is 313 newtons sine of 53. And that's FWY, sorry. Pesky subscripts. Gives us 550 newtons. So that calculated out as positive, so we were correct in our assumption that FWY is positive, because otherwise, if it was down, that would calculate out as negative, because I assumed it was upward. But I'm not looking for the X and Y components, I'm actually looking for the magnitude and direction of the force. So we're not quite done yet. I'm going to put those up here. All right, so basically what we have is we have FWX and we have a larger FWY, and we're looking for the magnitude. So we can basically just set up a triangle here. So we're going to have an angle theta between them. We're going to find the resultant. So FW is the Pythagorean theorem, so it's going to be FWX squared plus FWY squared. So FW is going to be the square root of FWX is 188 newtons squared plus FWY 550 newtons squared, which calculates out to be about 581 newtons. And then if I want to find the direction, that direction theta, I would use theta is tan to the minus 1. The opposite side is going to be FYW. The adjacent side is going to be FWX. So that's going to be tan to the minus 1 of FY 550 newtons over 188 newtons. Calculates out to 71.1 degrees. So, and I would say 71.1 degrees to the right and above the horizontal would be the most specific. But so that gives us a chance. So you see, we had to use the net torque equation to find tension. We then used the Fx and Fy equations to find the components of the force of the wall. We used the Pythagorean theorem to find the magnitude of the force of the wall, and our arctan to find our angle theta. Very typical problem. So there's some additional videos here. There's more on using the cross product and just in general how to calculate torque. There are some more examples on rotational equilibrium, especially another ladder example, so you can kind of see how those work if you need more help. And those are accessible by opening the links in the PowerPoint itself. Have a great day.